What if we are looking at finding the product of two vectors? It turns out that when we add vectors or subtract vectors, we're able to just add or subtract the x, y, and z components and have that mean something geometrically. Unfortunately, when we try to find the product of two vectors, it turns out that one, you can't just take the product of the x's, y's, and z's separately and have that mean anything in the context of geometric application. And secondly, it turns out that there's two different types of products that we could actually do. So we're going to look at the first one here, called the dot product. Okay. And when you look at the dot product, we're just going to be answering the question about how you are going to be able to find an angle between two vectors. So let's say that you have a vector u and a vector v, and we'd like to find the angle between these two vectors. So again, we could picture these as two different forces that are pulling in two different directions, and we're tasked at finding the angle between the two. Okay. Now it seems a little peculiar to start it off this way, so what we're actually going to do instead is we're going to do a geometry problem by connecting the two tails together. And at this point, if we were to make a vector pointing in this direction called w, then we should be able to see that v plus w is equal to u. Which makes sense because when you add vectors, remember you're just adding the tail to the tip of the previous one. But notice what else that means. It also means that w is equal to the vector u minus the vector v. Okay? Well, keep in mind by the law of cosines that if we wanted to find the angle, we could combine the magnitudes of each of the sides of these triangles in a particular way. So you might remember by the law of cosines from trigonometry, that if we wanted to find that angle, then I start by just finding the magnitude of w squared, which is the side opposite the angle. And the law of cosines looks a little bit like the Pythagorean theorem, where we could say that the magnitude of u squared plus the magnitude of v squared is equal to the magnitude of w squared, but that's not, because there is an extra term here that we have to subtract. It's minus 2 times the magnitude of u times the magnitude of v times cosine of the angle between. I'm going to put that in red here because our whole goal is to be able to start with vector u and vector v and find theta. So this right here is just nothing more than the law of cosines from trigonometry. So if you've forgotten that, I encourage you to go back and review that law. But this is purely for us to be able to derive the angle between these two vectors. Okay. Well, let's go ahead and start to compare a couple of things here. Let's remember that u, vector u, is simply going to be u1, u2, u3, right? Which means that if we want the magnitude of u, then that would be the square root of the sum of each of those squares. So why don't we recognize that the magnitude of u squared is going to be u1 squared plus u2 squared plus u3 squared. And I'm going to be able to replace that magnitude of u squared with those quantities in 1 second here. We'll also be able to recognize that the magnitude of v squared is equal to, well, same idea, v1 squared plus v2 squared plus v3 squared. And in a couple minutes, we're going to be able to replace the magnitude of v squared with that quantity. But what about the magnitude of w squared? So we need to keep in mind that w is u minus v. And since we're given u and v, and not really what w is, then what we're going to do instead is we're going to recognize that the magnitude of w squared is going to be the difference of each of those quantities, u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared. And now what we're going to be able to do is just combine those by merging everything together. So we're going to go ahead and manipulate this equation first. I'm going to add this term to the left, and I'm going to subtract the magnitude of w to the right, just to rewrite this in a bit of a different way. So we're going to write this as 2 times the magnitude of u times the magnitude of v times cosine of theta, and that's going to be equal to the magnitude of u squared plus the magnitude of v squared minus the magnitude of w squared. And now what I'm going to be able to do is replace each of these magnitude squareds into this side of the formula over here. All right, so let's go ahead and work that out. Since this is going to take a bit of space, I'm going to jump way over here. We're going to say 2 times the magnitude of u times the magnitude of v times cosine of the angle between them is equal to, well, I'm going to leave this right now as just the magnitude of u squared plus the magnitude of v squared. And what I am going to do is I'm going to replace this magnitude of w squared with what that turns out to be. Okay, well, it's u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared. Now we're going to notice that if we expand all of that quantity out, that we're going to see some quantities that are going to cancel out with these magnitude of u squared to the magnitude of v squared. Okay, so let's go ahead and do that. So we still have 2 times the magnitude of u times the magnitude of v times cosine of theta. And now this right here turns out to be u1 squared plus u2 squared plus u3 squared. The magnitude of v squared turns out to be plus v1 squared plus v2 squared plus v3 squared. And now we're going to expand each of these quantities right here. So when we expand that out, multiplying u1 minus v1 times u1 minus v1, we get u1 squared minus 2u1 v1 plus v1 squared plus. Well, we're now going to expand u2 minus v2 squared in the exact same way. Multiply it by itself to give u2 squared minus 2u2 v2 plus v2 squared. And now we're going to expand u3 minus v3 squared, which gives us plus u3 squared minus 2u3 v3 plus V3 squared. Now that looks crazy, and I get it, okay? But what we've got to realize here is this minus sign right here meant that we were subtracting all of those quantities. So this plus sign shouldn't be a plus sign. We should be subtracting all of this quantity over here. So when we subtract all of that, notice what's going to happen. We're going to be canceling out u1 squared minus u1 squared, u2 squared minus u2 squared, u3 squared minus u3 squared, v1 squared minus v1 squared, v2 squared minus v2 squared, v3 squared minus v3 squared. And so what's going to happen here is that all we're left with are these three quantities. So let's rewrite what we have. We have 2 times the magnitude of u times the magnitude of v times cosine of theta equals, and now all that's left is 2 u1 v1, 2 u2 v2, and 2 u3 v3. But notice that if I distribute the negative, all that's left is 2 u1 v1 plus 2 u2 v2 plus 2 u3 v3. Now I realize this looks pretty crazy, but remember what our whole goal was. Our whole goal is to find the angle between the vectors. So we need a little more space here, so let's go ahead and take a look at what's left. So we're going to manipulate this a little bit to get that theta by itself. So if we divide out the 2, okay, now notice that all that's left is the magnitude of u times the magnitude of v. And I just want to remind you about the arrow. I know it's still early in the semester, but it's important for you to recognize that every time you write a vector, you need to get in the habit of writing that arrow up above it. Notice that I didn't put the arrows here because those are just scalars. Those are the components of the vector, while this is the vector itself. All right, so I divide 2 on both sides, and now I'm left with u1 v1 plus u2 v2 plus u3 v3. And the last thing we have is that cosine of the angle between the vectors is equal to u1 v1 plus u2 v2 plus u3 v3 divided by the product of the 2 magnitudes. Now it's actually not that bad of a formula anymore. What we're basically saying is if you give me 2 vectors, u and v, from our picture up above here, if you give me 2 vectors and I want to be able to find the product, or I'm sorry, the angle between the 2 vectors, then all I need to do is apply this formula right here. Now this is assuming, remember, that u is equal to the vector u1, u2, u3, and v is the vector v1, v2, v3. Now remember, the whole point of this was to be able to find this thing we call the dot product. So far, we haven't even mentioned the dot product. But what I do want to mention now is this numerator right here. This numerator, where it appears like I multiply the 2 u values together, I'm sorry, the 2 x components together, and then multiply the 2 y coordinates together, and then multiply the 2 z coordinates together, and then I simply add all of those results. That comes up so often in calculus, in multivariable calculus, that we give it a name. And it turns out that the name of this quantity right here is the dot product of U and V. Or in other words, U dot V. So we say that the dot product of U and V is just the product of the x's, the product of the y's, and the product of the z's added together. So that means that we now have this new formula that says that cosine of an angle is equal to the dot product of two vectors divided by the magnitude of U times the magnitude of V. I'm going to state that in a slightly different way. The angle between two vectors can be found by saying that cosine of that angle is equal to the dot product divided by the product of the magnitudes. And there you have it. So the dot product turns out to be a scalar. Okay, think about why. If I were to find the dot product of two vectors, for instance, let's go ahead and maybe do an example here first, just so you could see what's going on. Okay, let's say that we have two angles. I'm sorry, two vectors. And we now want to find the angle between the following two vectors. Okay, let's say that U is equal to I minus 2J minus 2K. And remember, that's just called standard unit form or unit vector form. And then vector V is equal to 6I plus 3J plus 2K. Okay. Well, apparently, if we want to find this angle, all we have to do is apply the formula here to say that cosine of that angle must be equal to the dot product between the two vectors divided by the product of each of their magnitudes separately. Okay, well, I'm going to start with the denominator because that's relatively simple. I know that the magnitude of a vector is just the square root of some quantity. So I know that I'm going to be multiplying the square roots of two different quantities, the magnitude of U and the magnitude of V. I know that the magnitude of U is just 1 squared plus -2 squared plus another -2 squared. And the magnitude of V is 6 squared plus 3 squared plus 2 squared. So that takes care of the denominator. That's the product of the two magnitudes. But now if we wanted to calculate the dot product between the two vectors, now we're actually just going to be taking the product between 1 and 6, the product between -2 and 3, and the product between -2 and 2. Notice that all I've done is I've multiplied the x components together, the y components, and the z components. And after I'm done, you add the results. So that's by definition what we're calling the dot product. The dot product is just this numerator that ended up popping up and finding the angle between two vectors. And we're going to see in other circumstances, this comes up so often that we end up just giving it the notation of U dot V. All right. So what that means is that we could just simplify this a little bit by calculating the numerator and denominator. We get that cosine of theta is equal to, well, 6 minus 6 minus 4 divided by the square root of 9 times the square root of 49. So that gives me -4 in the numerator, and in the denominator, 3 times 7 is 21. Now notice that all that's saying is that cosine of some angle, cosine of the angle between them, is equal to this ratio. So now we're thinking back to trigonometry and recognizing, when is cosine a negative number? Right, now let's just think about that for a second. Remember that if cosine is negative, cosine is only negative in the second and third quadrants. So looking at a diagram here, if we were to take a look at a graph, okay, keep in mind that if you have some angle in the first or second quadrants here, that an angle in the first quadrant has a cosine value that's positive, while values in the second quadrant have a cosine value that's negative, right? So that must mean that if cosine is negative, then theta is greater than 90 degrees. Why don't we rewrite that in a better way? Just say that theta is greater than 90 degrees. While if we have cosine is less than or is greater than 0, then that means that theta is less than 90 degrees. So we can assume that by the fact that cosine of theta is negative 4/21, that our angle between the two vectors is going to be obtuse, bigger than 90 degrees, which means that theta is equal to cosine inverse of negative 4/21. And when you punch that into your calculator, you get approximately 1.76 radians. And notice 1.57 radians is 90 degrees, okay? So because we're typically, when we're dealing with trigonometric functions, we write things in terms of radians instead of degrees. It's typically better for us to not use degree measurement in describing our boundaries, but instead recognizing that pi/2 is going to be the same as 90 degrees. So that means that if cosine of theta is negative, then theta is greater than pi/2. And if cosine of theta is positive, then theta is less than pi/2. Now there is one thing to note as well. And when we came up with this formula to find the angle between two vectors, we noticed that u dot v had one notation here. We did see that u dot v was defined to be just the product between the x, y, and z components added together. So that's the standard kind of definition of what we expect the dot product to be. It's just the sum of the products of the x's, y's, and z's. But it turns out that there is another way to think about the dot product as well. If I want to get u dot v by itself here, I could also just multiply both sides by the magnitudes, okay? So that must mean that we have that the dot product could also be thought of as the magnitude of u times the magnitude of v times cosine of theta. So it turns out that these are both interchangeable. They mean different things. If we have the two vectors, then I could actually find the dot product in this way. But let's say I don't have the two vectors, and instead I have their lengths and the angle between them. Well, then I could use this formula to find the dot product instead. Okay? So there are a couple of important things to note about this. Okay? One thing to recognize is that sometimes the dot product tells us, if the dot product is negative, we found out that the angle is going to be greater than pi/2, greater than 90 degrees. If the dot product is positive, then the value will be less than, or I'm sorry, then the dot product would be less than, the angle would be less than 90 degrees, okay? However, one thing to recognize is that let's say I look at 90 degrees. what if theta equals pi over 2? Well, if theta is equal to pi over 2, then that would mean that cosine of pi over 2 is equal to the dot product over the product of their magnitudes. But we know that cosine of pi over 2 is 0. And if you really think what's happening here, I now have the fact that a fraction is equal to 0. The only time a fraction is ever equal to 0 is when the numerator is equal to 0. So that must mean that if the numerator is 0, then the angle between the two vectors will be 90 degrees, or pi over 2. So if theta is equal to pi over 2, then that must mean that the dot product is equal to 0. So we now have this beautiful statement here, this definition, that tells us that if you take the dot product between u and v and it ever equals 0, then theta equals pi over 2. But that tells us something else. It tells us that u and v are considered orthogonal vectors. Orthogonal means nothing more than just perpendicular. Orthogonal is the word for perpendicular when we're referring to vectors. Okay? So u and v are orthogonal. This is a really big deal, okay, because it's saying that if you're trying to find out if two vectors are orthogonal, all we really have to do is compute their dot product, and if the dot product turns out to be 0, then I know that the two vectors are orthogonal. So if u dot v equals 0, then u and v are orthogonal vectors. Now that we have a definition of the dot product, we can learn a few properties that the dot product holds. The first one that should be pretty obvious is, and before we do so, maybe I should remind you that the dot product is simply equal to the product of the x components of the two vectors plus the product of the y components plus the product of the z components. Well, considering addition and multiplication are commutative, then that must mean that the dot product is commutative as well. So u dot v will always equal v dot u. Hopefully you can see why that makes sense, because all that would mean is that I'm taking the commutative property of each of these terms. Okay, that's a pretty obvious one. Let's go through 2, though. This is a little less obvious. I won't prove this one, but it is kind of interesting to see because it's a form of the distributive property. Let's say that I want to take the dot product between u and the sum of two other vectors. Now, in general, what I would have to do is add v and w together, but keep in mind that when I add v and w, I can add those in any order based on the commutative property. And if I take the dot product, now I'm just multiplying the x component times the x and y and z, or the x component of x, y, and z components of u to the x, y, and z components of v plus w. So it appears that what I'm really able to do is just take the dot product between u and v and the dot product between u and w and add those together separately. So look at how that's really just the distributive property, but the distributive property over addition makes sense because of the fact that the dot product is found by just using addition and multiplication. So it appears that I should still be able to do that same thing. All right, let's look at the next one here. If I were to look at the 0 vector, keep in mind what the zero vector is. The 0 vector is different than 0. The vector, remember, has a magnitude and it has a direction. The 0 vector is the only vector with no magnitude and no direction. So really, if you were to graph this zero vector, which by the way is the vector 0, 0, 0, obviously it'll have a magnitude of 0. And if it has a magnitude of 0 and there's nowhere to point, then it has no direction either. So it's a really special vector. But if I were to take the vector, or the 0 vector, and dot it with any other vector, well, considering one of these vectors will, or one of these components will always be 0, 0 times anything is 0, which is why I'm left with the 0 vector. I'm sorry, not the 0 vector, just 0. Because of the fact that because a dot product is a scalar. So always keep in mind that if the dot product is a scalar, that taking the dot product of two vectors turns into a scalar again. All right, what if we wanted to take the dot product between a scalar multiple of a vector and another vector? Well, if you just multiply c times a vector, wouldn't that just mean that I would have an extra factor of c tacked onto each of these? So that would imply that I really could just pull the c out if I want to. I could also move the c onto vector v if I choose to. Either way I choose to do this, because matrix multiplication, I'm sorry, because dot products of vectors is commutative, I could think of this as vector u times c times vector v, or just pull the c out and recognize that it's the dot product between u and v. All right, and I guess I should probably put a dot between these as well, just to demonstrate that it is still a dot product. So whenever you're multiplying two vectors, it doesn't make sense to just multiply vectors. So that's why we always put a dot to demonstrate that it is in fact a dot product. Okay. And this last one, I think, is one of the most surprising results. If you take u and dot it with u, let's just think about what that would look like in general. That would mean I'd have u1 times u1 plus u2 times u2 plus u3 times u3. But then that would just be u1 squared plus u2 squared plus u3 squared. And that kind of looks like the formula that we use for a magnitude, which implies that it sure enough is. The dot product of u dotted with u is nothing more than the magnitude of u squared. And that's a pretty helpful result. Anytime you're taking the dot product with the dot product between a vector and itself, all that's left is the magnitude of u. Now it should be pretty obvious why. Because if I have two vectors that are the same, then the dot product, I should be able to recognize the angle between those two vectors is 0. If I go back up here to my diagram here, to my formula, okay, then if the two vectors are equal to, if the two vectors are the same, then that means that each of these v's would turn into u's. So that would mean that this would be u dot u over the magnitude of u squared. But notice that that would mean that the angle between the two vectors is 0. And if the angle between the two vectors is 0, cosine of 0 is equal to 1. So that would imply that u dot u over the magnitude of u squared is equal to 1, which implies that if I cross multiply, I end up getting that the magnitude of u squared is equal to u dot u. Okay, and so that's one little side note. Okay. You can now see a really cool application of the dot product when it comes to an application for force. So here we see a picture of a girl that's pulling a wagon. Now it seems like a very typical situation of you know, a kid playing at the, you know, playing with a wagon, or a parent pulling their child in a wagon. And the main thing to recognize here is that this is actually a vector being pulled upwards. So you should be able to see that this girl is pulling at a particular angle with the direction of motion being right here. So this right here is the direction of motion. Let's call that vector v. Now let's call this angle, or the vector that she's pulling up at, vector u. Now we should notice that there is a particular angle in between these two. And so how much of the force that she is enacting on this wagon is actually being used to pull in the direction of motion? Because some of it is actually going in the direction of motion. Some of it is going, in fact, in the direction of motion. But some of it is not. Some of it is going in the direction upwards. So some of the force is going in the direction of motion, some of the force is going upwards. How much of that diagonal force is being applied in the direction of motion? We refer to this here as the effective force. Now I'm going to draw this, or I'm going to redraw this, just so that we could actually see this without the girl here in the wagon and get a little confused. So we're going to draw this again. Okay, we're going to draw one vector here. Okay, that's going to be vector v. And we're going to take another vector right here, and this is going to be vector u. And let's label this as vector u, and this is vector v. Okay. Now the effective force can be found by doing what we call projecting the vector u onto the vector v. Now there's all kinds of ways to take the tip of u and have it hit v. All kinds of ways. Okay, it could come straight down, it could come out here. But what we want to do is we want to project the tip of u onto v by making sure that when it hits v, it makes a right angle. Okay, and when it makes that right angle, right there, the vector that remains is referred to as the projection. The projection of u onto v. So there's no difference between this effective force and this vector called the projection of u onto v. Okay? So that projection of u onto v is really what's going to be used in order to find how much force is being applied in the direction of motion, as opposed to the girl pulling up on the wagon right here. Okay? And notice as well that the hypotenuse of a triangle is always the longest side. Each of the other two sides are always going to be shorter. So that means that this force is always going to be less than the amount of force that's being pulled by that wagon or by the girl. Okay? So we want to look at this in a little bit different way as well. Okay? So let's redraw this picture here. Draw it again. Okay. Only now what we're going to do is we're going to now not label these by the vectors themselves, but we're going to label them based on their magnitudes, okay? So what their lengths are. So if I now look at this length right here as being the magnitude of u, okay? then I should recognize as well that if this right here was the angle between them, right, then I should realize that cosine of theta is equal to the adjacent side over the hypotenuse, which must mean that this side is the magnitude of u times cosine of theta. So that right there is now the length of the projection. So that just demonstrated what the magnitude of the projection vector is going to be, the magnitude of the projection of u onto v. And so this is still vector v down here, right? I've still projected it onto vector v, only now what I've done is I've found what the actual force is, how much of the force is being applied in the direction of motion. So the projection of u onto v then has a certain length and a certain direction. Okay, so the projection has length equal to the magnitude of u times cosine theta. And it has a direction. Now remember how to calculate direction. Direction is a unit vector. The projection is going in the same exact direction as vector v. So it must be a scalar multiple of v, but remember the direction is a unit vector. So that must mean that the direction is nothing more than v over the magnitude. So we could recognize now that the projection of u, or the projection of u onto v, can be written as its length or its magnitude times its direction. It's the same thing we did when we were looking at velocity. Velocity could be written as speed times direction. Magnitude could be, projection could be written as the magnitude times direction. So if we were to write that out, the magnitude is the magnitude of u times cosine theta times v over the magnitude. Now we're going to write this in a few different ways because there's going to be some really helpful tools to help us to recognize what we're actually trying to do here. Okay, so the first thing to do is recognize that the projection of u onto v is a scalar multiple of v. It's actually going to be going in the same direction as v, so it should be some scalar multiple of v. So with that said, why don't we go ahead and rewrite this projection then by writing it as a scalar multiple of v. The projection of u onto v can then be written as the magnitude of u times cosine theta over the magnitude of v. So all I've done is I've moved the magnitude of v over to here times vector v. So the benefit of writing the projection in this format is because we could see how long or I guess I should only put it underneath the scalar multiple part. So this right here, this value describes how long the projection is the projection compared to v. So if this turns out to be something like 5v, then that means the projection is 5 times as long as v. If it turns out to be 1/2 v, then that means the projection is half as long as v. So that's one benefit of writing it in this format right here. So you might be wondering, well, a few different ways to think about the projection, okay? Let's say that I had, well, if u was shorter than v, then I was able to look at the projection in this particular way over on the right side here, okay? But there's different ways that you could think about the projection as well. Maybe you have V is right here, and U is much longer. Well, if I wanted to look at the projection of U onto V now coming down onto V, I never hit V. So what I have to do is I have to extend V just so that I'm able to get a 90-degree angle. And now I should realize that this vector here is the projection of U onto V. So it's possible for the projection to be shorter than V, as is the case in this situation. It's possible for the projection to be longer than V, which is the situation here. It's also possible for it to go in the exact opposite direction. Maybe V is right here, and maybe U is back here. This all has to do with what the angle is between the vectors. So if the angle is acute, then I should realize that the scalar multiple will be positive. But what if the angle is obtuse? Well, now if I project U down onto V, again, there's nowhere to touch V. So I have to extend V backwards until it becomes a 90-degree angle. And now I should realize that the projection is lying in the exact opposite direction of vector V. So there's all kinds of ways for the projection to be geometrically demonstrated here. And that's why this quantity right here, this coefficient, tells us a lot about how long that projection is in comparison to vector V. Okay? So the bottom line, the projection is always some scalar multiple of vector V. But I'm going to do a little bit of fancy footwork here just to demonstrate that there's another way that you could actually look at this too. Okay? What if we were to do something a little peculiar here? I'm going to rewrite this formula. I'm going to say, let's say we have the projection of U onto V. And we still have this formula. We have the magnitude of U times cosine theta over the magnitude of V times vector V. I'm going to do something a little odd. I'm going to multiply this here by the magnitude of V over the magnitude of V. Okay? The benefit of doing this now is that you'll see something very helpful up top. Earlier on in this lesson, we learned that this here is another form for the dot product of U and V. I could rewrite magnitude of U cosine theta times magnitude of V as just U dot V. So that means that there's another formula that we could use, which is going to be U dot V divided by the magnitude of V squared times vector V. And this formula is actually beneficial because in order to use this one, we need to know the angle between the vectors so that I could plug in something for theta. Here, I don't need to anymore. I don't need to know the angle. All I need to know are the two vectors, and I could still find the projection. And more importantly, even though this is a really helpful formula as well, it turns out that there's an even better formula. Because notice, if I were to take out one of those magnitude of V's, and I have U dot V over the magnitude of V, and I now take out one of those magnitudes and put it underneath V over here, notice what we've done again. This is the direction. That's a unit vector, so that describes the direction of the projection. While this right here is nothing more than the magnitude of the projection. So we actually have two different formulas for being able to find the magnitude of the projection of u onto v. One of the ways that we could list the magnitude of the projection is just from our original diagram. The original diagram showed that the magnitude of the projection was just the magnitude of u times cosine of the angle between them. But keep in mind that we typically would need to know the angle between the vectors, and sometimes that's a pain to find. So instead, we now have a new way to do it right here, which says that all we need to do to find that magnitude is to take u dot v and divide by the magnitude of v. So just so we could see what we typically are going to use for our formula, the projection of u onto v will normally use the formula right here in calculating the projection. Just understand that different formulas are helpful in different circumstances depending on what we actually are given. Let's take a look at an example relating to the projection that we just learned. Now the projection, keep in mind, is just an application involving the dot product. So just like finding an angle between two vectors is a use of the dot product, finding a projection is also a use of a dot product. And so we've got two different questions here. First of all, it says find the effective force of some force given, called F, in the direction of V. So you can picture that as the wagon. The girl pulling the wagon is F, but the direction that the wagon is moving is V. So what we're doing there is actually finding a vector, finding a force called the projection. Then it says also find the scalar component of F in the direction of V. That's a fancy way of saying find the magnitude of the projection. Because what we're doing at that point is saying the scalar component is how much of the force is being put in the direction of motion, okay, or is being applied in the direction of motion. So that means that we just need to find for the first part the effective force. And the effective force is simply the projection of the force called F onto the vector V. So let's use our formula. Our formula is just u dot v divided by the magnitude of v squared times vector v. But it's not u anymore because there is no u, so that's why we're going to be taking f dot v over the magnitude of v squared. Okay. Well, I'm going to keep this in terms of v for a second, and we're just going to actually apply the formula. So f dot v, that's just going to be 5 times 1 plus 2 times -3 divided by the magnitude of v squared. Well, that's the square root of 1 squared plus -3 squared. Now, notice what's nice about squaring a magnitude. When I square a magnitude, I'm squaring the square root, which cancels it. So notice that this is still times vector v. So what I'm left with is -1 over 10 times v. Now I want to stop for a second here and just think about what that implies. We're moving in the direction of v. So what is the effective force in the direction of v? Well, it's -1/10 the size of what vector v is. So because it's 1/10 the size, that means it's much smaller than v. And because it's negative, it means it's moving in the opposite direction of v. So that tells us quite a bit here, but it's actually not the final answer yet until we multiply -1/10 times what vector v actually is, which is I minus 3j. Therefore, the projection of vector f onto v is equal to -1/10 I plus 3/10 j. And that's our projection. Now we're not quite done yet because we're still being asked for this this whole scalar component of f in the direction of v. So let's do that. Okay. So if I'm trying to find the scalar component of f in the direction of v, then keep in mind that all that's saying is find the projection or the magnitude of that projection. How big is that going to be? Okay. Well, so let's go ahead and put that down here. I was a little lazy about not wanting to rewrite all of that. So let's find the scalar the scalar component of f in the direction of v. Well, that's nothing more than just the magnitude of the projection of f onto v. Now we have a couple of different formulas. We have actually lots of different formulas. One way we could do it is just find the magnitude of what I just found. That's one way. Another way is to actually find the magnitude by using one of our two formulas. So keep in mind we had two formulas here. We had one formula that said we could find it by saying the magnitude of u times cosine theta. There's an issue with that though, because that would mean that I would need to have an angle between them. So I prefer not to use that formula. So there was another formula that said that I could take the dot product of the two vectors. I should stop using u because there is no u here. So it would be the magnitude of f times cosine theta, but I don't know the angle between them, so that's a poor formula to use. So maybe I use the dot product of the two divided by the magnitude of v. That's not such a bad formula, especially considering I already got what the magnitude of v is. So why don't we use that one? Okay. So we know that this is going to be the dot product between the two vectors. So f dot v divided by the magnitude of v. Well, let's take a look at this. We already got the dot product between them. The dot product was found way up here. It was -1. So we know that this scalar component is going to be -1 over, and the magnitude of v we already found as well. That was the square root of 10. Now be careful, it's not 10 because the magnitude of v was being squared up in this first formula, but now we're just saying the magnitude of v, and so notice that this right here is the scalar component. So the scalar component, or the magnitude of the projection, is -1/10. Okay, so sometimes you have multiple methods or options in terms of how to find a projection magnitude. Now, one last thing I'd like to note about the projection is that if I were to add together the projection plus this orthogonal vector right here, which right now I'll just call W for the time being, if I were to add the projection plus W, I would end up getting U. So that must mean that that orthogonal vector is simply going to be U minus the projection. So sometimes you're going to be asked for the orthogonal vector, which typically would be telling you how much force is being applied upwards. So again, if you think back to the wagon example, that would mean that the projection says how much force is being applied in the direction of motion, while the orthogonal vector would be describing how much force is being applied vertically. Okay? Now there's one last example, or one last application, an application for the dot product, that is, referring to what we call work. Now, there's actually a numeric or algebraic definition for what it means to say how much work was done in doing some particular task. So let's say that you're pushing a car. Let's say you run out of gas and you need to push the car. When you push the car, a couple of things come into play. How much work did you need to do to push the car? Okay, well, there's a couple of things that come into play. Number one, how heavy is the car? How much force are you going to have to apply? That's one thing that could come into play. Another thing is, how far do you have to push it? Are you a mile away from the gas station, or are you 100 yards? Okay, it's obviously going to the amount of work is going to be dependent on how much force you're going to have to apply and how far you're going to have to push it. Okay, so when we refer to the work done by a constant force, okay, work done by a constant force F, or a constant force with a magnitude, because we're talking about the amount of force that I have to actually apply. So let's call that the magnitude of F. And moving an object through a distance d. Is the following. Now, before I just tell you what it is, we're going to look at a diagram, or we're going to look at this a little bit more in a little more detail to get an idea about what this is. Well, by looking at this picture, the same idea that we had with the wagon pull, for instance, is how much work is the dad doing in pulling his daughter in this wagon? Well, first of all, we determine that the amount of force that's actually being applied in the direction of motion is considered the magnitude of F times cosine theta. Okay? But notice as well that I'm pushing for a distance d, or rather pulling if it's the wagon. So in general, the work done, if the force is directed in the direction of motion, work is nothing more than force times distance. Right? If it was a distance of 1 foot, then the work would just be whatever the force is. But if I have to push for 100 feet, it would be 100 times what the force is. So it's a scalar multiple, essentially, of what that force is. But notice in a lot of circumstances, the force is not in the direction of motion. This would be in the circumstance if you have a distance right here, and the force, you're like pushing a car, and the force is actually pushing in the direction of motion. The problem is that's not always going to be happening, okay? And so what if they are not in the same direction? Well, that would mean in this case that the work would equal the magnitude of F times cosine theta times the distance, which is times the magnitude of d. But again, that should look very familiar to you, because we learned that anytime you multiply the magnitudes of two vectors times the cosine of the angle between them, that's nothing more than a dot product. So just like we saw that in general, work is equal to the force times the distance, now we see if we have any two vectors at any two angles between them, the work is always the force dotted with the distance traveled. So that would allow us to now apply any sort of problems involving work. So we see that the dot product, just as a recap, the dot product of two vectors is a scalar. It's a real number. But its use is in finding the angle between two vectors. It's in being able to find the projection of a vector onto another vector. It can be used in order to find the work done in pushing or pulling something over a given distance. So, and not only that, it could also be used to determine if two vectors are orthogonal. We learned that if two vectors have a dot product of 0, the two vectors are orthogonal. So this dot product is a very helpful operation when it comes to vectors, and we're going to see it pop up in a lot of different circumstances as we move forward, So the most important thing to do is just kind of get all of the formulas that we learned in this section down pat, so that you can know when to use it and what time.